Algebra 2, Module 3, Lesson 26, percent rate of change. We've kind of talked about this before, I feel like, but now we're going to talk about it more in depth. So we're going to develop a general growth decay rate formula in the context of compound interest. So these next few lessons we're going to be talking about interest, which is very applicable to your life because you're going to be buying cars or houses, all this type of stuff that's going to have interest, and it's going to have compound interest. And so you need to see how it works so you can manage your money correctly. Students compute future values of investments with continually compounding interest rates. So what that means is you want to buy a car that's cost, I don't know, $50,001 or $50,000. How much do I need to be saving now so that when I turn 18, is it 18 for y'all when you get a driver's license? 19. So let's say you're going to want to buy that car when you're 20 then. So you're saying, all right, I want $50,000 saved up when I turn 20. How much do I need to put in now so that it will grow to be $50,000 when I'm 20? Or how much do I need to put in today and then add to it every month? $50 or $100 or whatever. So that's what we're going to be talking about. A little bit more applicable, practical stuff for y'all. So, when we're looking at this, this is what you're wanting to focus in on. For application problems involving a percent rate of change represented by the unit rate R. R is unit rate. We can write the function of t, where t is time, is equal to principal, the initial rate, times 1 plus the rate to the t power, where f is the future value or the ending amount. Okay? So it's what we want. It's that $50,000 that we want to buy that car. Okay? P is the present amount or principal. It's what we put in initially. It's the initial amount that we're going to grow from. Okay? And T is the number of time units. And now that is, time units is what people normally get confused on. So when the percent rate of change is negative, R is negative, and the quantity decreases. So that's when we have a decay, right? If we got a negative rate of change, then we're losing money. Okay? The nominal APR is the percent rate of change per compounding per period times the number of compounding period per year. If the nominal APR is given by the unit rate R and is compounded n times a year, then the function future time or future amount of time is equal to P times 1 plus R over n to the n times t. That's the key point there that most people forget. You've got to put it, you got to divide by it, but you also have to multiply by it. Okay? Or not multiply by it, you have to set your time by it as well. Okay, so this describes a future value at time t of an account given that is given nominal APR and an initial value of P. I know all you're going, what is this guy talking about? It's all right, just calm down. We'll get there. Now, for continuous compounding, which we like continuous compounding, okay? As long as we're not paying interest. As long as that's going into our bank account, that's great. But if we're getting charged compounding interest, bad, okay? We can write it as F is equal to P, E being Euler's number to RT, where R is the unit rate to the percent rate of change. Okay? If you can, after we're done with these, you should be able to go back and read that and go, oh yeah, got it. Know what that's talking about. All right, page 2. All right, this says a youth group has a yard sale to raise money for charity. The group earns $800 but decides to put the money in the bank for a while. Their local bank pays an interest rate of 3% per year, and the group decides to put all of the interest they earn back into the account to earn even more interest. Okay? Now, if you look at this, look at 0 years. That's kind of like our initial amount, right? That's what we're putting it in. Now, if we multiply that, so 3% of that would be how much? $24, right? So we could have said 800 times 3% or 0.03, and that equals $24. We don't want to do that, okay? Because now we just got to do an extra step. Now we have to add the $24 back to that original amount. So remember when we had 1 plus R in that previous page? Okay, that's what we want to do. So we would multiply 800 times 1.03 because that 1 accounts for 800, right? If we do 800 times 1, we got it, and then the 800 times 3% is all together now. So we kind of skip a step there. So make sure you're putting the 1 in front of it there. All right? So now we have $824 after that first year. Now we just move it down and multiply it by another 1.03, and then we get $848.72, and then we just move that back down, multiply it, and we just keep going that way. We take whatever we make and we put that money back into it. We just keep, what we would call that is reinvesting. Take whatever you make, reinvest it. Take whatever you make, reinvest it. Lynn's buying that $50,000 car. She puts it in, gets interest the first year, takes that money out of interest. Well, now that money's just sitting there it's not gaining anything. So why wouldn't she just keep reinvesting it? Because that's going to help grow her bank account for her, or her savings account for that car, right? So keep reinvesting that money. Now, in this first or second column here, where it says balance in terms of last year's balance, that's just taking the previous year, multiplying it by 1.03, right? And so that's what this says. The bank account last year times, so it's last year's amount. Okay, you see that? M minus 1. The year minus 1. The previous year times 1.03. Now, over here on the last column though, let's look at what's going on here. Notice that all of these are staying the same. All these are 800. But we're still getting the same amount over here. How are we doing that? Now notice, we have 800 initially, and we do the same thing, same step right here, 1.03. And we get 824. So we're good there. But now the next step, instead of taking the previous year's amount, we're using the original amount. It's kind of like saying we don't care about the previous year because we're basing everything off of our original amount. So now we're going to have to multiply by 1.03, which would give us the first year's amount. But then we're going to multiply again by 1.03 because we want to include the previous year's amount. We're not just doing 800. We're doing 800 times 1.03, which gives us the previous year, times 1.03, which will give us this year's amount. But there's an easier way to write that. Can we not write that as, this would be 800 times 1.03 squared, right? 1.03 times 1.03 is 1.03 squared, right? Well, in this next one, we would write it as 800 times 1.03 times, or to the third power. Now, what is 2 and 3? Notice how that correlates with our year. So now, all you need to know is the original amount and then whatever year you want. So say we're going to keep it there for 5 years and I'm getting a 3% interest every year, then I can say 800 times 1.03 to the 5th power. And now I know how much money will be in that bank account after 5 years. Okay? See how that's a little bit easier than having to know the previous amount? We don't have to keep going back and forth, back and forth, back and forth, back and forth. All right. No. Page 3. All right, it says, here we are, it's basing it off of the previous problem, or the youth group problem from example 1. Notice what it says. They're investing their money at 2.976% interest per year. Now this is compounded monthly instead of depositing it in the original account earning 3.0% compounded yearly. Okay, so it's less of percentage, but notice that it's compounded monthly, not yearly, monthly, but with a less percentage. Or we can compound yearly with 3%. Okay? Now, with an initial deposit of 800, how much would each account have after 2 years? Would anybody want to take well, we can look, let's go back. We can actually figure, after 2 years, go back to the chart, because we've already got one of them, right? How much was it? We've already got the 3%, and I just lost connection here. How much? Let me see if I can find it here. Okay, so let me go back here. All right, we would have, after 2 years, if we look at the previous page, it was $848.72. So compounded yearly would be $848.72. All right, now we need to compound it monthly. And now this is the trick. This is the tricky part where I said you got to pay attention or you're going to miss. All right. So what we're going to say is, what do they call it? F of t is equal. What are we starting with? Starting with the 800, right? Okay. We know we got to do the 1 plus. Now, we're doing 2.976%. How do you write that as a decimal? 0.02976, right? Everybody good with that? Divided by what? What are we going to divide by here? This is the R divided by N. What is the N? N has to do with the number of times it's going to happen within a year. Well, if we're doing it monthly, how many times is that going to happen? How many months are they in a year? 12. So now we have 12 down here, And now remember we said we have to multiply that by our t. Okay, what is t here? What? Year, but how many years? 2. So now we have to do 12 times 2. Okay, these numbers right here. Let me do a different color here to make it pop. These numbers right here have to be the same. Have to be the same. Okay? Now, you plug that in your calculator, get your answer. And what is it? We plug that into the calculator, we would get, I think, let me see, $849. But how? We had a smaller percentage. We weren't doing it by 3. So how in the same time span of 2 years is there more money in this account than there would be in this account? What's the factor? But the percentage is lower. How do we have more money? The other one was 3%. What is the main factor here? This formula is simply 800 times 1.03 squared. It's because in this first one, the one with the 2.976%, it's compounding monthly, not every year. So after January, there's not just $800 in the account. There's probably like $800.15 or whatever it is. Well, then that much is going to compound for the month of February, and then for March, and then for blah, 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 all the way up for the years. Okay? So it's compounding more frequently, and therefore we're going to get more money. Okay? If the percentages are close. 3 and 2.976 really close. So you can say since that one's compounding more frequently, then it's going to be a higher value. Okay? Now, B says compare the total amount from part A to how much you would have made using the 3% rate compounded yearly for 2 years. Which would you recommend to use? Well, okay. We've already done that. All right? So what are you going to recommend? If you're making 28 cents extra, which is not a lot, right? In 2 years, just think 10 years down the road where that might be. Okay, I know it doesn't sound like a lot, but when you're compounding monthly or even daily, that's going to add up to being a whole lot of money. Okay, so don't think, well, it's only 28 cents. Whoop-de-doo. 28 cents over 10 years is a whole lot of money. Okay. So we would definitely go with the 2.976% account. All right. Is there page 4? There is. All right. This is one of the problems from the assignment or from your homework. I'm going to go ahead and do it with you. So pay attention. It says, consider the 2 bank accounts. Bank A gives simple interest on the initial investment in savings accounts at a rate of 3% per year. Now, I probably need to go ahead and give y'all, I may try and do that today, give you a vocabulary sheet, because we've not dealt with simple interest. What is simple interest? It's not compound interest. Okay? So it's not compounding daily or monthly or anything like that. Simple interest is just how we got this year, we're going to compound it in 1 year. Okay. So simple interest, just think of it as just 1 year's interest. Okay, a rate of 3% per year. Bank B gives compound interest on the savings account at a rate of 2.5% per year. Okay, find out the following table. Now, simple interest. Remember I said it just counts for that 1 year. So what that means is, if you put in $1,000 with simple interest, remember we're not compounding it with the previous year's amount. You are only getting interest on that $1,000. Okay? Just $1,000. So if we did that, we would say 1,000 times 1.03%? 03. And how much is that? What's 3% of 1,000? $30? Yeah, $30. So this would be $1,030. Now remember, we don't get to count that in next year's. We do not count $30 in the next year. We are simple interest. We're only getting $30 every year. We only get to count that $1,000. So how much is going to be in the account after 2 years? 1,060, 1,090, 1,120, 1,150. Now, here's what's happening. Here's what that bank doesn't tell you. Okay? They're giving you simple interest, but they're taking the money that you put in your account and they're putting it into an account that they're getting compound interest on. So they're basically taking what you should be making from compound interest and putting it in their pocket, and they're giving you the $30. You're only getting $30 each year. So the first year, they don't make any money. But that second year, they're taking that extra $30 of yours, and they're getting interest on it. That's how they make money. Okay? They take what you give them, they invest that money, they give you a little bit to make you happy, and then they pocket the rest. Okay? See how that works? Now, let's look at Bank B's balance. Now, where you get compound interest, okay, but it's still only happening once a year. It's not monthly, it's just 1 year. 1 year compounded. So, and it's at 2.5. So we could say 1 times 1.0, not 1,000 times 1.03 to the first, or T, and we know that that's going to be $1,030, right? No, it's not, because we're not doing 3%. We're doing 2.5. So it's not going to be the same. So let me do that. Can somebody do that right quick? Or actually, here, I got it over here. $1,025. Okay, so we don't have as much, but guess what? We get to take that $25 and count that this time. So if we do that again, now we've got $50, which is not as much. .81. Now we're getting to be a lot more. And oh wait, that's not right. That's not the same. That is not the same years. Sorry. That is not the same year amount. Let me see. I don't want to have to do all this, so let me find it. It's simple once you figure it out. Just put it in the calculator. We're going to make sure. Okay, $25 and then this is $50.63. $76.89. You need to be able to make sure that you're able to use your calculator to get the correct answers. 81 and 5 years, we have $1,131.41. Now, let's look at this. Even though we're compounding our money, we still don't have as much, do we? $1,150 is more than $1,131.41. So you say, well, why would you do compounded interest with a lower percentage if you're not going to have as much? It's crazy, right? Because it's going to have an effect over a longer amount of time. Okay, so here's what you're going to have to realize whenever you're doing this with bank accounts. You need to think, am I going to have this for 10 years? Am I going to have this bank account for 10 years, or am I going to have it for 20 years? Okay? If you have it for 20 years, compounding interest is probably going to pay out a whole lot more. So, it's over a matter of time. So let's answer these questions right quick. It says, what type of sequence do Bank A balance represent? What type of sequence is that? Y'all remember talking about sequences? Remember, whenever we use the previous amount and we're just adding something to it, it's called an arithmetic one. Arithmetic and geometric? Yeah, geometric sequence is the other one. So that one is just because the difference is only adding $30 to it. So that's called an arithmetic. Okay, arithmetic. We're just adding to it. Now, don't think about your formula. You just want to look at your answer. Okay, we're just adding $30 to it each time. So that's an arithmetic. We're just adding. Now it says give both a recursive and an explicit formula for Bank A. Y'all remember this? This is we skipped this lesson where we did it in the past, but I skipped the lesson that was recent because I really don't care if you can write it in recursive or in explicit formulas because there's really certain ways that you need to write certain equations. But anyway, I'll do this right quick. Let's do this for B. A recursive, think of it as reoccurring. Okay, so this would be, you have to talk about A1, your starting point. So your initial point is 1,000, right? Well, now your formula is going to be AN is equal to AN minus 1, which means the previous month or the previous year, the previous term, whatever the previous term is, what? Plus 30. Okay? As long as I know the previous term, I can give you an answer. Think of that's your recursive formula. Now, explicit is this is the easy one. We don't care about the previous term. Okay? Because I can figure it out if I have the previous term or not. But you still have to do your due diligence here. You got to say A to the N, which is our original amount, or is 1,000. Okay. But now then, how can we write an equation dealing with our 1,000? How would we do that for A? It'd be 1,000 plus what? Plus 30. Now think about what is N in this term. What is N? That's as many years, right? So we would just say times N. So if I want it for 5 years, what's 30 times 5? 150. 150 plus 1,000 is 1,150, right? So there's your recursive and explicit formulas. All right. C, what type of sequence do the bank B balance represent? Well, it's a little bit different, right? We're not just simply, I can't look at 125 or $1,025 and go to $1,050.63 and then go from $1,050.63 to $1,076.89 just by adding a common term. I can't just add $25.63 to it every time. So now we know that that one's going to be a geometric term or sequence, geometric sequence. All right. I'll go ahead and do D just to give you a recursive for it. How you get a recursive and explicit from a geo. Okay. So now recursive, remember, we're talking about what? Cursive, previous amount. So we're going to have to define what is the previous amount. Previous amount was, what do they call it? B. Okay, they're doing B1 is equal to what? Well, that's equal to 1,000. That was our initial amount, previous amount. But now what are you going to do? Just look at our formula, the one that we used. We used B n minus 1, right? I'm sorry. Hold on. Let's do B n equals B n minus 1 times 1.025. Okay. I can take the previous month's amount or previous year's amount, multiply it by 1.025, and get my answer every time. As long as I know the previous year's amount, I can do one step, multiply it by 1.025, and we've got it. So instead of adding to it, geometric, you're going to multiply or divide by it. Okay. So whenever you see a recursive formula for a arithmetic sequence, you're going to add or subtract. If you see a recursive formula for a geometric sequence, you're going to be multiplying or dividing. Normally you're going to just multiply, but you multiply by either a decimal or a whole number. Okay. Now, how would we write an explicit one? This means we don't care about the previous year's amount, and we just want to give an answer based on time. How would we do it? If you know, please speak up. These are tough. I get it. Remember, we just care about B to the N because we don't care about the previous year's amount. How would we do it, though? It's on the page. It's already on there. It's right here. We did an explicit formula right here. We said 1,000, well, sorry. I guess we need to say B, oh, no. Sorry. We need to do Bn is equal to 1,000. And then we would say 1,000 times 1.025 to the t. However many years, put that as the power of the exponent, and we're done. Okay? So it says, which bank account is increasing faster in the first 5 years? Well, that one's easy. Bank A, right? Bank A is increasing faster in 5 years. If you were to recommend a bank account for a long-term investment, is 5 years long-term? No. You're probably going to talk about 20 years being a long-term. Okay? So, what would you recommend? If you're thinking long term, compounded interest is going to work out every time if it's a close percentage. Now, if you're getting 10% more on another one, then that's probably not going to work out. But if it's a close interest rate on the two accounts, long term will always be better for compounded interest. Okay. Now, so we're going to go with B here. And it says, at what point in the balance of bank B larger than the balance in bank A? Now, how could we figure this out? Anybody? We just got done doing these. How could we do this? Remember when we set numbers equal to each other? Okay. So if we did that, if you look at this graph over here, can y'all see the line? So somewhere like right here, it overtakes it. Okay. Compounded interest is more above that line. Below the line, the simple interest is a better account. So here, what is it? Well, here's 15 and here's 16. So during the 15th year, so after 15 years, you're going to have more money in your compounding interest account than you would in your simple interest account. Okay?